Chapter 17 Notes, Part 3. Today we're looking at capacitors. If you ever took apart any electronics piece of equipment, you'll see one of these components. They're called capacitors. A capacitor is a device used in electric circuits to store charge. Pause and copy. Basically what it is two parallel plates. And when we hook a voltage supply to it, it starts to build up charges. And it takes a while to build up, and it's building up more and more charges on the plates, and there is a potential being built up between them. And it keeps charging until the voltage between the two plates equals the voltage of the battery. We say the potential between the plates equals the potential of the battery. Once we take the battery away, that potential stays there. So we have stored a charge on the capacitor now. And I can put some kind of electrical equipment onto it and run some electricity from it. And eventually wear that charge down. And once the charge is gone, the electricity is gone, and we're back to two parallel plates again with no charges, and it starts over again. Pause and copy. This is a formula for capacitors. Q is the amount of charge that is built up on the plates. It's the electrons on one plate and missing electrons on the other. And V is the potential difference of the source. That would be the voltage of your battery that you're hooking to it. Now C is called capacitance, and the capacitance comes with your capacitor. If you look on the capacitor, it's stamped on the side. This is 100 microfarads. Farads is the units that the capacitor is measured in. The capacitance for a particular capacitor cannot be changed. However, you can make a capacitor with a different size that has a different capacitance. A farad is defined as a coulomb per volt, and those just come from the units in this formula here. The capacitance, basically, it's telling you how much charge the capacitor can hold for a given potential voltage that you put across there. Pause and copy. The capacitance depends on several things. One is the area of the plates. The bigger the plate, of course, the more charges that you can build up on it. And also the distance between it. The smaller the distance, the stronger your capacitance will be. So this is a formula that will calculate what the capacitance is depending on the area and the distance between the plates. This symbol here is called the permittivity of free space. And this is the permittivity for a vacuum that we would plug into the formula. They eventually figured out that if we put an insulating material in between the plates, it serves a couple purposes. One, we can make the plates a lot closer together and not worry about them touching. And two, that material will cause a higher capacitance. And I'll show you how that works in just a second. That insulator inside there is called a dielectric. And there's a constant that goes with the dielectric. You look it up in a table, and we multiply that by this number, the permittivity of free space, to come up with the permittivity constant that we're putting into the capacitance formula. So this is a table. I copied this one from your textbook. This is the dielectric constant, and this is the electric field that's being built up inside of the capacitor. Pause and copy. So let's look at how this works. Here's a capacitor. We have our basic parallel plates. We are building up a charge on them, and in between the charge is electric field that goes from plus to minus. When we put the dielectric inside there, the dielectric is an insulator, and that means all of the atoms are randomly spaced and the electrons are not allowed to move. However, the atoms can rotate, so their negatives are lining up with the electric field. We say that the insulator is polarized with a charge separation. What this process does is basically cancel out the field in certain areas inside of our insulator. So the field is being reduced overall. And looking at our field formula, if we have a smaller field, that makes a smaller voltage or a smaller potential difference between the two plates. So V is reduced. And looking at our capacitance formula, if we have a smaller V, that's going to make a larger capacitance. This is not something you need to be able to explain, but since it uses a lot of terms, you do need to understand how parallel plates work, and this is polarizing an insulator is something that we've done in the past. Uses for capacitors: defibrillator when they're zapping somebody to bring their heart back to beating again after it has stopped, charging a flash on a camera, and actually the keys on your keyboard are all little capacitors. So here's the formulas for potential energy stored inside the capacitors. There's 3 different versions. The first 2 are on your AP sheet, and the last one you can make by substituting the QVC formula into one of these 2 formulas. About this time, I have students that are getting into the WTF mode, which is, what's the formula mode? We need to know what the formulas are used for. These formulas, they're on your formula sheet, are only used for capacitors. You cannot use them for anything else. End of notes.